Okay, so for this section, we're going to look at simple harmonic motion. Okay, so there's quite a lot on this first page for us to have a little chat about. Okay, just some of the key points that we need to consider and things like that. Okay, and then we're going to jump into an example. So the key thing, very similar to your normal differential equations, is setting up your diagram. So let's make sure wherever your fixed points, so your origin is, okay, we need to make sure that we have our acceleration, our velocity, and our displacement all in the same direction, okay, which is going to be away from it. Okay, now what's really, really important, okay, and this comes up quite often, is us like proving if something is simple harmonic motion or not, okay? So to do that, what we need to try and do is get my equation to look like this. Okay, so I've got my x double dot, which my acceleration is equal to minus omega squared x. Okay, now omega squared can be a number. Okay, it could be anything like that. Okay, so that's what we're trying to get in the format of. Okay, now to get this, we're going to apply Newton's second law. Okay, and then we're going to rearrange it and we're going to solve it from there. Okay, until we can get it to look like that. So that's the key bit about with our simple harmonic motion. Okay, so that's our basic definition. Now, once we get this, there's a few things that when we've got a oscillation. Okay, let's say this is my origin by here. Okay, and let's say we have a thing called our amplitude. So we have our amplitudes which are either side. This would be minus a. This would be positive a, for example. Okay, so amplitude is how far it bounces back between. Okay, and we have some key points. Okay. So when it's at its origin, so here, okay, it should be at its maximum speed, okay? Now we do have an equation for its speed here, okay, for any given, but we can simplify that and find a maximum speed as well, okay? My maximum speed is simply omega a. Okay, now omega is, again, just the value we get from up here. So once we've found our simple harmonic form like this, then we need to make sure that we find omega straight away and we can use it, okay? So at these end points, okay, so my point up here and my point down here, okay, this is where my velocities are going to be zero, okay? So this is where it kind of gets to this point. It's slow. As I go past O, I should be at my maximum speed. And I'm going to slow down and down and down even more until I reach A when my velocity is zero, and I'm going to bounce back. Okay, so I'm decelerating when I'm moving outwards, and then I'm accelerating when I'm moving inwards. Okay, and then I'll be decelerating, accelerating, okay, and things like that. So that's what simple harmonic motion looks like. Now we can have it in a vertical way as well, with like a string and things like that, okay? But we'll tackle a question like that later down the line, okay? Now from here, we know how to do general solutions, okay? Now a general solution generally is always going to look like this, okay? So for a normal general solution for the differential equation is this. So x is p cos omega t and q sine omega t, okay? Now, these little t's are just time periods, okay? Now, we also have the period, which is another equation for us to remember, okay, which is 2 pi over omega, okay? So if our amplitude is how far it comes out, a period is how far basically it gets to do one full amount. So if it starts at the end, for example, it's how far it gets to go all the way down and back up again. Or if it starts in the middle, it's how far it gets to do everything. So one full period, okay, of completion. Now, we do have some other special cases, okay, which are in this blue box by here, okay? Now, we can quote these whenever we want them, okay? So we don't have to, we have this general solution here, which is great, okay? But if it fits one of these special cases, we can use these, okay? So first of all, when time is zero, so basically where it starts, okay? So if time is zero and it's at its amplitude, so it's at the end, and its velocity is zero. So for example, let's say it was attached to a string, I pulled it to A, I held it here, and then I released it. That would be this first special case here. X is at its amplitude, velocity is zero, and its time is zero. Okay, then we have another one when it's at the middle and its velocity is greater than zero, so it's moving. In this case, it's moving to the right. when t is 0. Then I'm going to have this one here, which is a sine omega t. And we've got the other version in which it's moving the other way, so it'd be minus v. And that's when it's going to be minus a sine omega t. So these last two are very similar. Okay. We can quote those as much as we want. Okay. So all these equations here, I can kind of quote when I need them. Okay. But quite often, as I said, we kind of have to prove this first one. Then we got the speed one down here. So we got v squared is omega squared, and then a squared minus x squared. Okay, that's my velocity at any point. And I can again quote that when I need it. Okay, so kind of my key points. Okay, so one means oscillates between minus a positive a and minus a with a period of 2 pi over omega. The maximum speed is just omega a. Okay, this is when x is 0, so when it's at its origin. Okay, the maximum magnitude of the acceleration is omega squared a, and this is when it's at its either end, so at a or minus a. That's when it's got its greatest acceleration. Okay, but velocity is also 0 at that point as well. When x is 0, the acceleration is 0. This means that x equals 0 must be an equilibrium position. Okay, that's when it gets back to the middle. So let's jump into this question here and let's have a go at it. So I've got a particle p moves along the x-axis at time t. The displacement is given by this equation by here. Okay, prove that p is moving in simple harmonic motion. So again, if I want to do this, I need to get it in the form of x double dot equals minus omega squared x. Okay, to do that, I'm going to start with my x, which is 12 cos of a 13. Now, I could think about applying Newton's second law, but I don't know any forces, so I'm going to follow this route instead. What I'm going to do is I'm going to go, that means x dot, and I'm differentiated, is going to give me, cos is going to go to minus sine, and divide by a third, sorry, I'm going to times by a third pi, so I get 4 pi sine a third of pi t. And I'm going to go hit, now let's find x double dot, okay, which is going to give me minus 4 thirds pi squared, and then cos of a third pi t. Now, when I get to this point here, I need to try and find this factor in it. Okay, and if you look, I've already got the cos. Okay, so what I'm trying to do here is I'm trying to get into this format. So I'm going to leave x double dot there. Okay, and I'm basically going to need to have in a bracket 12 cos a third pi t. Okay, that's what I need to have, because then I can go, okay, look, this is x and this is omega. Now there's a minus here. Now I've got pi squared I also need to have. Now I need to make it 12. I've currently got 4 thirds. Okay, so to make that 12, I need to have it over 9. So if I did pi squared over 9 and I times by 12, I'd get 4 thirds pi squared. Okay, and there you go. That's the format I want. Okay, so that is minus pi squared over 9 x. Okay, which is exactly in the format I want. Okay, so therefore, simple harmonic motion in the form x double dots equals minus omega squared x. Okay, now I'm going to state my omega as well. So omega must be pi over 3. Okay, that's going to be important for me to do that so that I can carry on with the rest of the questions. Okay, so if we need to prove it, differentiate again, try and get your x out and think about what you need to times that the original by to get to it. Okay, so next one, find the period and the amplitude. Okay, so in this scenario, let's use t very quickly. It's going to be 2 pi over omega, which is just going to give me 6 seconds. Now my amplitude for this one should be fairly straightforward, because if we look, this here can only go between minus 12 and 12, because no matter what values I put into cos only goes between minus 1 and 1. So my amplitude must be 12 in this case. Okay. Right, C, maximum speed. Okay, so max speed is, we can quote it, is omega a. So it's simply going to be pi over 3 times 12, which is going to give me 4 pi meters per second. Okay, yes, I could times it out. That's completely fine if you've done that. Okay, but I don't need to necessarily. Okay, right, and then find the time taken by P to travel from 60 to minus 6 root 30. Okay, so all I'm going to do, okay, is I'm going to basically plug these two bits here. Look, here's an x and here's the x. I'm going to plug it into this original equation. Okay, I'm going to find my two times. I'm going to find the time between them. Okay, so let's do the first one. This one's when it's 6. So at A, x equals 6. So I'm going to have 12 cos of a third pi t. Remember, let's make sure we're in radians because we've got pi's involved in here. Equals 6. So that means t would have to be 1 in this case. Okay, then let's do at B. X is going to be minus 6 root 3. Okay, so I've got 12 cos of a third pi t is going to equal minus 6 root 3. And again, let's solve that for t. It's going to give me 5 over 2. Okay, so it's taken 1 second to go from its center to 6, and then it's taken 5 over 2 to go from the center over to this distance here. Okay, so let's think about what this is. It's 1 second to get to 6, and then it's 5 over 2 to do this kind of movement. So I simply want the time between them, okay? So time is going to equal 5 over 2 minus 1, which is going to be 3 over 2 seconds, or 1.5, however you've written it is fine. Okay, either or will give you the correct answer. Okay, so key kind of like thinking behind it, use your x dot, x double dot to prove that it is simple harmonic motion. Sometimes we'll apply Newton's second law, and that'll depend on what forces are acting on it. In this case, I wasn't given forces, which is why I went down this route for pi. From there, we can quote all our things for your period and your amplitude, and then your maximum speed as well. And if you want a time taken between two certain distances, find the time at one distance, find the time at the other, take them away. Okay, so those are the key points to do with our simple harmonic motion. Okay, in the next video, we're going to look at one where we've got a string and it's like vertical and we put it down. Okay, and we'll look how we can tackle that question instead. Okay, but apart from that, okay, I will see you in the next video.